Hey everyone, welcome to The Explainer. I am absolutely thrilled you're here today because we are going to tackle one of the single biggest pain points in scaling multi-agent AI systems right now. If you've been building with frameworks like LangGraph, you know the power of chaining specialized agents together, right? But you've also likely hit a massive and honestly really expensive wall when it comes to scaling them up. Well, today we're looking at a fascinating solution called PrismLang that is a total game changer. It completely changes how agents actually talk to each other under the hood. So 10 times. Let me ask you something. Are your AI agents secretly inflating your cloud API bill? Just think about a standard 10-step text pipeline for a second. An agent does some research, passes a full paragraph to a summarizer, then that summarizer passes an even longer blob to a reviewer, and so on and so forth. Because language models charge by the token, you are effectively paying 10 times for the exact same context to be reread over and over again. You aren't just paying for the AI's reasoning, you're paying a huge penalty just for repetition. Okay, let's dive into this and map out how we're going to solve this massive, expensive problem together. Here's our roadmap for the explainer today. 1. The token tax. 2. PrismLang middleware. 3. The Prism envelope. 4. Vector compression. And 5. Business outcomes. Let's get right into it. Section 1. The multi-agent token tax. We really need to define what exactly goes wrong when an assembly line of AI agents relies entirely on bloated, raw text. And this brings us to the core of the problem, the token tax. In a multi-agent graph, every single hop between your agents usually requires resending massive chunks of context. In real benchmarks, a typical inter-agent hop using raw text can easily exceed 391 tokens per transfer. When you multiply that across a graph with dozens of nodes, it acts as a compounding tax on every single interaction. Even if the new info added at a specific step is tiny, you're still paying full price to move the entire history. Because of this text bloat, development teams end up hitting 3 massive walls. First, you get those runaway costs from repeated context we just talked about. Second, there's no structured audit trail. When routing goes wrong, your engineers are stuck guessing or digging through totally unstructured logs. In regulated industries like healthcare or finance, simply saying, oh, the model routed it incorrectly is absolutely not an acceptable postmortem. You need real traceability. And third, shared context equals shared risk. In multi-tenant SaaS applications, passing huge text payloads doesn't naturally enforce data isolation, which is obviously a major security headache. Which brings us to my absolute favorite quote, and the central philosophy of this whole explainer. Stopping for text, start routing with math. This brilliantly illustrates the paradigm shift we're about to explore. Instead of shipping whole paragraphs between agents, what if you could just ship a compact, auditable mathematical envelope instead? Section 2, Introducing PrismLang middleware. So, let's officially introduce the solution. PrismLang is completely free, published under the Apache 2.0 open source license. Now, the crucial point here is understanding where it actually fits into your stack. It is not a replacement for LangGraph. Think of LangGraph as the highway system, and PrismLang is simply a highly efficient compression format for the cargo on the trucks. Your highway stays exactly the same. Your StateGraph, node functions, conditional routing, and checkpointers, all of that stays. But what you gain is staggering. 57 to 62% fewer prompt tokens per graph run, a dedicated rule chain audit trail, and cryptographic tenant isolation. And you get all that just by adding one decorator to your existing nodes. Section 3. The Prism envelope solution. We know what PrismLang is, but let's dive into the actual mechanics of how this middleware packages the handoff data. I like to use a factory assembly line analogy here. Imagine replacing heavy, bloated, multi-page text memos between factory stations with tiny, scannable, mathematical barcodes. Each station, or agent, still reads and produces rich text to do its own specific job. But when it's time to actually hand off the work to the next station, it just passes along a compact mathematical fingerprint instead of the entire transcript. That barcode is what's called a Prism envelope. Let's walk through what's actually inside it. Instead of 391 plus text tokens, you get an envelope that is roughly 414 bytes. It contains a 64-dimensional vector fingerprint representing the text's meaning. It holds a category slug, like research or risk, to clearly show intent. It includes a rule underscore chain, which gives you an auditable record of exactly why it was categorized that way. And it carries agent ID metadata. Because these envelopes are stored in an append-only sequence, they create an immutable, chronological audit log for flawless debugging. Section 4. How vector compression works. So, how exactly does big, messy text turn into that tiny envelope? Let's look under the hood at the deterministic math that makes this possible. Now, what's really interesting here is that this compression process requires 0 GPUs. It completely avoids using another costly LLM call just to route data. Step 1, PrismLang locally encodes the raw text into a 384-dimensional semantic vector using ONNX runtime right on a standard CPU. Step 2, it applies a spherical blend, meaning it pulls that vector geometrically toward a specific category defined by your taxonomy, like pulling financial text toward a risk direction. And finally, step 3 is JL reduction, where it projects that 384-dimensional vector down to a super compact 64 dimensions. And that third step brings us to an absolutely crucial production detail: cryptographic tenant isolation. When that vector is shrunk down, the Johnson-Linden-Strauss projection matrix used to do it is totally unique to each tenant. It's seeded directly from the SHA-256 hash of the tenant ID. What this means in practice is that vectors from different tenants are geometrically separated in space, achieving a cosine similarity well below 0.20. Even if two different clients process the exact same text, their vectors won't look anything alike. This is true enterprise-grade data safety in shared infrastructure. Section 5. Real-world business outcomes. Okay, it's one thing to talk about elegant vector math, but let's look at the hard numbers. In highly regulated production environments, these reductions literally gut massive chunks out of monthly cloud API bills. We're seeing a 62% reduction in healthcare clinical multi-agent chains, a 59% reduction in trade market logistics graphs, and a 57% drop in finance risk and compliance pipelines. Just by changing how your agents hand off data, you're immediately saving a fortune on inference costs. And hey, the savings aren't just on the API side. Think about your graph state growth. It goes from this runaway linear text bloat to a tiny, fixed payload of roughly 320 bytes per turn. That massively reduces your RAM usage and completely solves the headache of PostgreSQL checkpoint bloat. Your infrastructure gets cheaper, and your recovery times get incredibly fast. Let's summarize this value proposition side by side so you can really see the impact. With text-based handoffs, you pay full token cost for hop. With PrismLang, it's roughly 60% less. Text gives you 0 structured routing audit trail. PrismLang gives you a full rule chain per turn. Text relies on application layer filtering for tenant isolation. PrismLang uses cryptographic mathematical seeds. And honestly, most impressively, text often requires extra LLM passes or GPUs for routing, while PrismLang handles it all deterministically right on the CPU. Replacing full paragraphs with math elegantly solves literally every pain point we talked about at the start of the explainer. So I'm going to leave you with this final provocative thought. If your agents must collaborate, why on earth are you still making them past heavy paperwork? Remember, at the very end of your graph, PrismLang's boundary translator reconstructs perfectly human-readable text for the user, all without an extra LLM call. Your users still get natural language, and your agents still reason in text. But internally, it is time to stop paying for text. Start routing with math and let your pipelines scale the way they were always meant to. Thanks so much for joining me on this explainer, and I'll catch you next time.